Topology is a branch in mathematics that studies the properties of geometrical spaces that are preserved under continuous deformations such as twisting, stretching, tearing, and opening holes. And this very first video of this lecture will focus on manifolds and their properties, charts, and atlases. A manifold M is a topological space, set of neighborhoods that locally resembles Euclidean space near each point, as we zoom to the very small scale. This feature allows us to study complex shapes and spaces using calculus and geometry. For example, we're living on Earth. Consider its surface as a loop, which is a one-dimensional manifold. However, we humans don't experience these bendings. As we zoom into the smallest possible region of the loop, it turns to be a straight line, which is a one-dimensional manifold. And the loop is a 1D manifold because we can also map points on the loop to points along the line using the angle in between. Locally homeomorphic to Rm, meaning that along each point P which belongs to the manifold M, there exists an open neighborhood U, such that U is a subset of M, and a homeomorphism phi that maps elements from the open set U into the n-dimensional Euclidean space or Rn. X of U's are the coordinate system on U of functions x's and chart on M having U, phi, where U is a chart domain and phi is a chart map. Hausdorff is another property, where two distinct points x and y which belong to manifold M having disconnected neighborhoods such that x belongs to U and y belongs to V, such that the intersection in between the two sets U and V is equal to phi, meaning that U and V are disjoint sets. It is also second countable, where there exists a countable basis for the topology of the manifold. But what is a basis? It is a collection of open sets B for a topological space X, such that a set of shapes can cover the entire space by overlapping them. For every point X belongs to the topological space X, there exists at least one basis element, small letter b, which belongs to B, such that X belongs to the small b. There will be always a basis element small b3 which belongs to B that fits within the overlapped two basis elements b1 and b2, such that a point x belonging to b1 and b2, then x belongs to b3, which is a subset of b1 intersection with b2. I mentioned previously the word chart, and now let's come to the definition. In a manifold M, a chart U, phi is like a map that takes out a small part of an abstract manifold to represent the points using familiar flat coordinates. But keep in mind that for a chart U, phi, U, which is a subset of the manifold M, is an open set in M. Phi, which takes the elements of U and map them into Rn, is the homeomorphism, where phi and inverse phi are both continuous. And in case of overlapping where the intersection between U and V is not phi, we can consider several chart maps. However, they have different coordinates, but they are all considered true. We can switch between these maps, and the conversion from chart map 1 to chart map 2 is called a chart transition map. To switch from map 1 to map 2, we do gamma after inverse phi. And from map 2 to map 1, we do phi after inverse gamma. An atlas is a collection of charts that covers a manifold. As each chart covers a different part of a manifold and maps the local coordinates for the area, switching them allows to navigate the entire manifold. The atlas is represented by the charts having U index and phi index, where the I index belongs to the index set capital letter I, such that the union of U index covers the whole manifold. However, there might be overlaps in charts, so the intersection between U and V must be equal to phi, and we have to attain this. So at least the functions gamma after inverse phi and phi after inverse gamma need to be continuous where I is compatible. Thus, an atlas is called a maximal if its chars are all compatible, meaning that the transitional map gamma after inverse phi is smooth, meaning that infinitely differentiable. And this was everything for now, and thanks for watching.